Okay, so we're going to be talking about acid and base equilibrium. So the equilibrium component is going to be exactly the same as before. Now I'm going to kind of talk to you about the different types of acid. So we have the Bronsted-Lowry acids and bases. So when we talk about acid and bases prior, we always talked about them being a proton donor and a proton acceptor, right? Yes, no?
Wasn't it just the hydrogen?
Yes, the hydrogen ion, which is just the proton. If you guys remember.
Sorry.
No, don't apologize. H plus. So you guys remember H plus. How many electrons does H plus have?
1.
Not H.
Oh, sorry.
Okay. We know that H has 1 electron. So how many does H plus have?
Well, you're losing the electron because it's positive.
That's right. So we have 0 electrons. Okay. How many protons does H plus have?
Well, wouldn't you increase? So it'd be 2 instead of the 1.
Would you increase? Why would you increase?
Oh, you're just losing, so it'd still be 1.
Okay, so it still is 1. Okay, and then how many neutrons does it have?
0.
Okay, so we know that it has H plus is just donating what then? If there's no electrons, if there's no neutrons, what are you getting when you have just H plus?
You're donating the proton.
You're donating a proton. Okay, so we've defined it as a proton donor. Okay, and up until this point, that's how we kind of gave that general definition. Okay, so let me kind of give you the distinction between the different concepts of an acid. Okay, so we have the Bronsted-Lowry acid, which we're going to be talking about prior. Arrhenius acid system is that concept of that proton donor, H plus being being donated. And then in the case of hydroxide, you have OH being donated. So Arrhenius just kind of looked at it as the hydrogen ion and the hydroxide ion. An acid always has a hydrogen ion, and a base always has the hydroxide ion. That's Arrhenius. And so that's the kind of system that we've kind of been used to from here on out. And that system, the pH system, is based upon Arrhenius. Okay. So when we talk about acid and bases, we know that acids, have you guys ever smelled vinegar? What does it smell like?
Bitter.
It's got a bitter. When we taste it, we know it's bitter or sour, right?
Yeah.
And it kind of tingles our nose a little bit, right? And if you guys had just concentrated citric acid, the same thing would happen, right? Most of your acids, there's a tendency, even though we tell you guys not to smell those things, or if you do, you do the wave test. I know all the time, I always have like 5 or 6 students that will stick their nose right above an acid. It'll be a strong acid and it burns the crap out of their nose, but they notice that it's sour. And then they realize afterwards that their nose is burning like hell because they took a big whiff of hydrochloric acid or something like that, which is a very strong acid. Okay, so acids and bases have basically been around forever. We know that acids are always going to have that sour bitterness to it, right? And then we know that just from doing pH, which you guys should be doing here soon, doing pH tests and what you guys have done, you know that litmus paper changes as a result of that. And a lot of that is due to dyes in plants. So dyes have various chemicals, and those chemicals can be altered by the addition of that hydrogen ion or that hydroxide ion. And so by those changes, we are able to sit there and determine pH visually by color changes. Or we use a potentiometer, potentiometer, or basically a pH meter, that kind of picks up the hydrogen ion to let us know what the pH is in that context. Okay. Let's see. So if we look at it, Arrhenius kind of gives us this very generic equation. HA represents just the general polyatomic ion or ion. H represents that H plus. When we get together, we get the H plus that ion that we're working with. And then we know that if the acid is strong, it's going to have a complete dissociation. So you end up with just the H plus and that ion. Okay. So in the case of an Arrhenius base, we have often a metal and the hydroxide ion. And so then we'll get that the metal ion and the hydroxide ion when it completely dissociates. And again, that's representative of a strong acid or a strong base. So you get complete dissociation. But we also know that in the case of weak acids and weak bases, that you don't get complete dissociation. And so you get some dissociation, but the majority of it isn't dissociated. So that's gonna kind of play a little bit different, okay? And so that means that we're gonna have some sense of equilibrium occurring. But Arrhenius looked at it as complete dissociation when we have acids, but that wasn't actually true. So it was very limited in terms of what we could do in that regard. Now the Bronsted-Lowry theory basically expands that definition. So remember when we talked about, now we have the hydrogen ion being a proton donor and the base being a proton acceptor. Okay, so if we look down here, we have ammonia. Ammonia is considered the base. Water, in this case, is considered the acid, because what happens when we put ammonia in water, we can get the ammonium ion and the hydroxide ion. Okay, so in this case, the acid is donating that H plus to the ammonia, giving us NH4 plus. Okay, so are you with me?
Yes, just the gaining and losing of the hydrogen.
That's right. Okay, and so this is it's broader than what we saw with the Arrhenius model, right? But just slightly broader, right? So in this context, one is going to be gaining a proton and one is going to be losing. One is going to be accepting a proton. Accepting, and one is going to be donating, sorry. Okay, as a result of that, we have it set up because on both sides of it, you have what we call an acid and a base. On the reactant side, we have this represents our base because it's going to be able to accept the proton. And then in this case, water is going to be acting as our acid because it's going to be the one that's donating the proton. On the other side, this now is called our conjugate base because it was the product of what was accepted by that base, right? And then this guy is called our conjugate acid. This guy's called our conjugate base, okay? Because if we look at it, the equation can technically go the other way as well too, right? Since we have these double lines, so really this line means this way and that way. Okay, so in this case, this guy is going to be accepting the H plus, and this guy is going to be our donor. Do you guys get that?
So it's just reversing the process that it started.
That's right. And the fact is that there is an equilibrium system that is in play, right? That you're going in both directions, okay? And so your forward reaction, forward representing this direction, and then your reverse reaction, okay? And there's going to be an equilibrium that's Okay, so identify the acid, base, and conjugate acid, conjugate base. Okay, who's going to be the acid, or who's going to be the hydrogen ion donor in A?
Would
Would it be the I want to say HNO3.
Okay, and we also know that that is nitric acid, right?
Yeah.
So then that means that water is going to be the what?
base?
Base. Okay, now who's going to be the conjugate acid?
It'd be the,
Oops.
it'd be that one.
Okay. And then what about the conjugate base?
The last one.
NO3.
Okay, what about the next one? B.
So the water is donating.
Okay, so then that's,
The acid.
okay,
The base.
okay, on the other side, this is going to be my conjugate acid.
That would be your conjugate base. Oh, wait, no, because hydroxide. Okay, hydroxide would be your
Okay,
base.
so we'll say C base.
My
And
bad.
then, so by default, C acid. Okay, what about when we get down here?
Well, you're creating, so you're creating the base, right? So, because it's hydroxide. You're talking about E?
Well, would H2O be the base?
Okay, so you said H2O will be the base. Are you sure?
No, hold on. Don't.
No, because it's donating. So that would be your acid and the oxygen would be your base.
Okay,
Oh yeah.
But then, so then that would be a conjugate base though, because you're creating hydroxide. Yeah or no?
I don't know. I'm asking. So are we
Out loud.
are we accepting the hydroxide or the base? Or
I think it would have to be a conjugate acid, right? Wait a second. Hold on. The H is there.
I'm saying base because it's hydroxide. But I don't know.
Yeah, I'm gonna have to go with base.
It is an acid.
okay, because if we look at the hydroxide, so initially we have the water, the oxygen ion as a base, and then that oxygen ion is now accepting one. So this guy is kind of an odd case. So your base
Oh my god, now it froze again.
is now accepting one of the,
Can anyone hear me?
I can hear
Yeah.
you. It's accepting that proton, right, that's been donated. So we went from a -2 to a -1. At the same time, it's also going to be our conjugate base as well. So one will represent the conjugate base and one represents the conjugate acid.
Because there's two of the molecules present.
That's right. So we have the water molecule, right, that donates So in one case, we're getting this happening. Right? Because it's donating that proton, right? So we go from a -2 to a -1. And in the other case, we had the water that was splitting, right? So we're taking this guy, and that's what actually is being donated there. And so we end up with this guy. Okay, so you have this guy represents your conjugate acid, your C acid, and this guy represents your C base. So if you look at it together, it's both.
Okay.
You see it?
Yeah, now that, okay.
A little tricky, huh?
A little bit.
Okay, so what about F?
Jeez.
Can y'all hear me?
I can hear you.
Oh, thank God. I was like, did it freeze again?
So which one is the acid and which one is the base?
So the first one is your base, the second one's your acid.
Okay,
And then that's your conjugate acid. And then your conjugate base is the last one.
okay. What about here?
Your would your NH2 be your acid?
That's your base because the H2S is donating. You can see it on the other side. It's losing.
Oh yeah.
And then the NH3 is gaining. So
So you're saying H2S is our acid?
yes,
Okay. I'm just asking. And then, so this is our base.
that's your base.
So this guy is,
The conjugate,
Acid.
yes.
are you sure?
No, it's the base.
Okay.
And then the NH3 is the acid.
Okay. Are you guys getting it? Is it clear?
Kind of. Wait, can we go back to the last one? Why was the HS the base and not the acid?
Why was the HN is the, okay.
No,
Because
the HS negative one.
HS the acid? Oh, this
The
one?
product.
Yeah, that one.
Okay, because now, okay, so best way of saying this. So if we look at this guy here, start over here. This guy is losing that H plus, right? So it's giving
Yeah.
up that H plus. This guy is gaining. So we know that this guy's donating, this guy's accepting, right? So if we look over here and we were going back the other way, this guy is now accepting the H plus, which means that it's going to be the base. And this guy is donating to get back in the other direction.
Oh, okay.
Okay, so then if you look at it, they kind of go in pairs, right? So if this guy was an acid initially, since it lost that H plus, now it's the base on the other side.
Oh yeah, I can notice. So that each one has their pair. Oh, okay.
That's why Abby, he said it reverses on the way back.
Oh, okay.
Yeah.
Okay, yeah, got it.
Okay, let's see. Let's see. Okay.
This wasn't making too much sense in the book, Dr. Henry.
The auto ionization of water.
Yeah, because they're like you're gonna disregard it, and some of the examples I think I remember I was like, what? But
Yeah, the book made it confusing. I did
was-
not understand at all.
Okay, so let me see if I can explain it to you.
Okay.
So what they kind of mean by auto ionization is it forms an ion independently, automatically, without any instigation or anything like that. The water itself basically always is in its ionic form. We have, or in a form of equilibrium. So you have water, as you have down here, shown down here, your liquid water. But it also, there's parts of it that's broken up, right, into ions. And so you already have ions existing. You have the hydronium ion and the hydroxide ion. Now, the hydronium ion is going to be at always at the same concentration for equilibrium. So it's going to be 1 times 10 to the minus 7 molar, always. The hydroxide ion is always going to be at the same concentration as well.
That's always at a specific temperature, right? According to the book.
Yes, but it pretty much holds true at all temperatures, although it can be slightly deviated on temperature, but for the most part, it's really close either way. So at the end of the day, right, your pH is just a concentration of your hydronium ion, or your H plus, okay? I'm sorry, minus the log. Cheating here a little bit. Minus the log, the concentration of your hydronium ion. So that's what your pH is equal to. So pH of water is always going to be 7 because it always auto-ionizes. Once it reaches equilibrium, which water is almost always in equilibrium, it's going to always end up being a pH of 7. And that's because if you take this number here, right, the log of 10 to the minus 7 is just going to be 7. Minus log of 10 to the minus 7 is going to be 7.
Yeah.
Okay. So you're always going to have a pH of 7. So basically, auto-ionization is just telling you, always it's going to be this, right? Okay. So when we talk about our cheat here, so remember when we were talking about equilibrium, and we want to calculate the equilibrium constant for water. So Kw is equilibrium constant for water. That's going to equal, these guys are both they're going to be the same coefficient, right? So you have, here you have 1 in front of it, 1 in front of that. So then it's just going to be the concentration of H3O plus times the concentration of OH, right? Because we know that water is a liquid, H2O is a liquid, so we're not going to take it into consideration for our equilibrium constant, right? Now, we know that these concentrations are always the same value. They're not going to change for water. So then we're going to get Kw is just going to equal 10 to the minus 7 times 10 to the minus 7. which equals 10 to the
Oh, that's where you get the 14th.
minus 14.
Okay.
Okay. Does that make sense?
Yeah, now it does.
Okay. So our pH scale is really based upon aqueous solutions. It's based upon about being in water. So pH 7, we call it neutral because 7 is that point where water is at. That's going to be our neutral ground. If we have a whole bunch, if we have majority of it being, if we have all of it being hydroxide, then this guy is going to be 10 to the 14th. So our scale goes up to 14 and it goes all the way down to 0, right? So if we have it all being pH, all of it being the hydroxide, it's going to be 0 in this case, right? So we can go from 0 to 14. Does that make sense?
Yeah.
Okay, let's see. Okay, so ampheteric properties or amphiprotic properties basically means that you have things that can either be a proton donor or a proton acceptor. Okay, so water is one of these guys. It can act both ways. In some cases, here, this guy, it is what's happening. What is water? Is it a proton donor or is it a proton acceptor?
It is accepting.
Okay, it's accepting. So in this case, it's going to be the base, right? And then this guy is going to be the acid. Where down here, is it a proton donor or is it a proton acceptor?
It's donating.
Okay, so then this guy is the acid. And then this guy is the base. You see how that works? So water can swing both ways. One of those magical traits that tend to be consistent about water, right? Goes to those plus charges, hey baby. Goes to those minus charges, hey baby. It can donate protons or accept protons. Okay. Clear?
Yes.
Okay, so we just talked about this. So the pH is equal to the minus log of the concentration of the hydronium ion or the H plus. And then the POH is going to be equal to the minus log of the hydroxide ion. And together, they're going to add up to 14. Okay. So if I know one, let's say if I know that my hydroxide ion is 0, then I know that my pH is going to be
It's not 7. Would it be 14?
it'll be 14, right?
Is it? Yeah.
So, and then if I know that my hydronium, so the way that my hydronium ion would be 0 is if, how can we get the log of 0? Well, I mean, how can we get a value that is the log of 0?
Would it be a negative? So like a negative, right? Because that'd be positive. So it'd end up being 0. So like a -7 already.
What is the, let's see, maybe I'm old and everything. What is the value of log base 10 would be -1. So what is the log of 1?
0.
Okay, so
it need to be 1 then.
yeah. So in that case, you're saying that all of the everything is pretty much going to be your POH, right? and then you have very little or no H available, okay? So if we had 0, if we have a pH of 0, so if our pH is equal to 0, pH equal to 0, then we know that this case, our pH, our POH is going to be equal to what?
14.
14, okay? So in that case, you're saying that all of the ions are H plus, and you don't have any OH minuses in that case. So does that make sense? I know that's not really intuitive there. Because you're saying, so 10 to the 14, we're basing our scale in this range. It goes from 0 to 14. If I have a really strong acid, right, it's 0 or lower than 0, that means that everything that I have in that solution is going to have H plus. We're not going to have any OHs in that situation, okay? And then vice versa, if it's 14, it's the pH of 14. Because we know that this value, KW, is going to be 14, right? And so since that's 14, if everything is this guy, your pH is going to be equal to 0, right? And so you're calculating, so in that sense, you're calculating the concentration of just your POH, right? So then it's limited to be 10 to the minus 14. That would be the concentration, which basically is a really, really low concentration. And then you're saying that this guy is a concentration of 1, right? If we take the log of 1, that's going to equal 0. If we take the log of negative 14 minus the log of negative 14, that's going to give us 14, right? So you're saying that all of those, basically you have none of them that are really, this POH is so low that it's not compared to the water. Are you with me?
Yeah.
Okay, so when we're just looking at water alone, the pH is always going to be 7. Okay. Okay, and so we define acids when we use pH. We use pH decision to define our acid and our base. So if our pH is 0 to 6.99, we say it's acidic, right? That's because you have more H plus ions than you have OH ions, okay? If our pH is greater than 7.01, then we have more what?
Base, hydroxide.
Okay. Okay, let's see if any of it made any sense. Complete the following calculations. Calculate the pH for 0.20 molar HCl solution. HCl is a strong acid that will completely dissociate.
So you take the negative log
Okay.
of your molarity.
Okay, so negative log of my molarity. So that's 0.220 molar. What do you guys get?
1.5. Oh, I did it wrong. Oh. 0.65.
$0.658.
Yeah, sorry.
Okay, so if we wanted to calculate the POH for 0.100 molar of sodium hydroxide. Okay. Calculate the pH of 8.0 molar. I'm sorry, calculate the pOH of 8.0 molar nitric acid solution. Nitric acid is a strong.
It was 1.8, Dr. Henry, not 8.
I'm sorry, 1.8. Thank you.
I got negative 0.255.
So that would be the pOH, right? So then what would be the, so if the that would be the pH is negative. You said negative what? 2.55?
Yeah.
2.55. So then what would be the pOH?
So
What is the max that it can be?
14 or 7 for each, so 14 total.
Okay, so then it could be 14. So if I got a value of 14, if my pH is negative 2.55, then my pOH has to equal what for it to be 14?
So would you just subtract the difference?
Okay. So then would it be subtract or would you?
Well, you're gonna add it, right? But
Yep. For this to be true, we have to add that value, right? So then it would be 16.22. Okay. What about calculating the pH?
Oh, going back to C, Dr. Henry.
Huh?
The reason why we found the pH first was because it was an acid, right? So that gives
That's right.
us, and then we had to take that and find the base.
That's correct.
Okay. Now I see what. Okay.
Okay. So calculate the pH for 0.400 molar of potassium hydroxide. Hydroxide is a strong base with complete dissociation. So what am I going to do here?
So it'd be the same thing, right?
Yeah, so we're going to have to calculate. In this case, we're going to calculate the pOH.
So 0.398.
So you get concentration of 0.400 molar. And that's, you said, equals 3.98.
No, 0.398.
Okay. And then we subtract 14 by that value.
So you're adding when you have pH, you're subtracting when you have hydroxide.
Yeah. Well, no, it just depends on the circumstances, right? So in both cases, you technically should be subtracting, right? But this guy was a negative value. You understand? So,
Okay, so
this
with the
equation,
negative, positive.
yeah, this equation always stands. We have pH plus pOH equals 14. Okay. So then in both cases, you're subtracting, but here you have a negative value, right? So when you bring it to the other side, it's going to make it a positive. Okay, so then you get
pH is 13.6.
Okay, calculate the hydrogen ion concentration for a solution of pH 7.4. So with a pH of 7.4, what am I going to do to calculate that?
Will we be doing the same thing I always have with the log?
That's right. In this case, we would set it equal to 7.4 equals that concentration. So negative log concentration of X, and we solve for X. So how would I solve for X?
Would we divide the 7.4?
We're gonna divide by negative log.
Yeah.
So we to solve for X. So is it negative log? Because it's log base 10. Okay.
Oh,
So
that's
then it's the same thing as saying negative, because we have negative 7.4, we bring the negative to the other side. So we have negative 7.4 equals log base 10. So then if we take this to the 10th power, negative 7.4 to the 10th, that's going to be the inverse of that, and that's just going to give us X. Do you understand? So
Oh, okay.
we know that the inverse of log base 10 is going to be, it's going to equal just 10 to the X. Okay. I think I wrote that wrong. Let me think about that. Okay, so then that's going to be our value for X. And what do you guys get? 10 to the negative 7 is what? 10 to the negative 7 power? 7.4 power?
4 times 10 to the negative 8.
Okay. Actually, I get 3.6, 3.999, oops, 3.98 times 10 to the negative 8. 1, 2, 3, 4, 5, 6, 7, 8. Yep. Molar. Okay. Calculate the hydroxide concentration for a solution with a pH of 11.2. So what am I going to do here?
We would do this basically kind of the same thing as we did with the first.
Okay. So now we want POH, and that's going to equal pH, oops, equal 14 minus pH. So then that's going to equal 14 minus 11.2.
0.28. Or 2.8, sorry, geez.
Okay, so then if we take the inverse of that, the inverse log, so then we'll get
10 to the
10 to the negative 2.8. It's going to equal our concentration of OH.
1.58 times 10 to the negative 3rd.
Dr. Henry, quick question. Where the hell did the 14 come out?
Because we know that water is always, it's always adding up, it's always going to add up to a KW of 14. So you're saying
Oh, okay.
pH plus POH will always equal 14.
Okay, okay. Got it.
Okay,
Okay.
good.
Yep.
So I'm gonna stop here. We'll pick this back up on Monday. I think I gave you homework assignments on here. I think your homework assignments have been shrinked, so they're not as intense as well.
Or do we have lab today?
So we need to do, yes, we will have lab today. We need to check our booze or our kombucha.
Okay.
Okay,
My booze is not bubbling.
it's not bubbling.
Mine either.
So we'll open it up and we'll see what's going on. Okay, so sometimes it just takes a little longer.
I'm actually headed out of town right now, Dr. Henry, so
I'll catch you another day.
Friday.
We can do it Friday. I'll set up a time for you.
Okay,
It'll be a perfect because then we can really sample the booze there.
we can see what's going on.
Well, you can't. You have to get your other half to do it.
This is unfair, I'm telling you, unfair.
Okay. So hopefully you guys will be able to make it later tonight for your sampling. If not, let me know and then we'll set up a time either tomorrow or on Friday for you guys to do that. Okay.
Okay. I'll see you tonight.
Okay, great. I'll see you guys tonight.